Very good. Arvid.
Should I share my screen?
Arvid, let me introduce you first. So welcome everyone. I don't think Joe needs a long introduction because many or all of you will know him. So Joe just finished his PhD with Yvonne, and he has been working on neutrino cosmology and to look at kind of how to solve it in an intelligent way. And he will tell us about that today in his talk. So please, Joe.
Okay. Well, where did my pages go? Here we go. Okay, thank you for the introduction. Yeah, so today I'll take you on I guess, a scenic route of the struggles in the past 3.5 years of trying to get neutrinos into embodied simulations in a viable way. So yeah, a lot of this work was done with my supervisor Yvonne and Amol, the postdoc with us, and okay, used to be with us, and now he's in Liverpool, but he's still a very big part of the process. Okay, so let's just get into it. I guess it's not a lot of like introduction or background motivation needed because we're dealing with a very standard scenario here. So we're only looking at standard model neutrinos. So there's 3 lepton flavors and just the standard 3 mass generations. And the question kind of in the room is this one that's been repeatedly asked, is that what is the absolute mass scale of neutrinos? We measured very well about the difference between the mass generations, but still need to find out exactly what the absolute mass scale is going to be. And there's a related question, like what's the hierarchy of it's normal ordered or inverted ordered? And normally you think these kind of questions will be a particle physics question. So you probably build like a detector or a particle experiment. So where does cosmology really come into this? Well, it turns out cosmology can do a lot for us in terms of neutrino physics because there's quite a lot of them up there in the universe. So neutrinos are thermalized quite early in our universe. So just after inflation and reheating would have produced all 3 generations. And now they're on average about 400 of them per cubic centimeter all around us. And given the abundance coupled with the fact that they are long-lived, so without any weird beyond standard model scenarios where they decay away somehow, if we just take the standard model neutrinos, they would have decoupled around the time of weak interaction decoupling. And from that point on was free streamed all the way to today. So in this long life, they participating almost every single epoch in the universe's evolution. So in the formation of the CMB and then later on in the formation of large-scale structure, the neutrinos would have had a big impact. And we can find these signatures in cosmological observables and learn a lot about what exactly the neutrino mass could be. And so for us, we're going to focus mainly on the large-scale structure side of things. So of course, in the CMB physics, you can already say a lot about the neutrino mass constraints. But if you think about the late time formation of structure, massive neutrinos having mass, so they will gravitationally interact with other matter like cold dark matter and potentially other dark matter candidates. And they will contribute to the clustering of and formation of structure, and that eventually will play host to galaxies and galaxy clusters. And we have a lot of experimental methods of observing these large-scale structure, even if we can't see the neutrinos themselves. And from these observables, we can infer a lot about what the sum of neutrino masses could be, because how heavy the neutrinos are will impact what kind of structure and how much structure is formed. So for example, in the CMB, okay, even though I said I wasn't going to talk about CMB, but the CMB photons, they come from the last scattering surface and have to travel a long way to get to us on Earth today. And during this travel, it will have to go through all of the structure in the universe and as it forms. So the gravitational potential will influence these photons via weak lensing. And you can then map out exactly where and how much of these gravitational potentials are out there by looking at how much the CMB photons have been lensed. And this lensing map will give you a handle on what the picture of the structures are, and in turn give you a way to say something about what the mass of neutrinos could be. And similarly, you can also do this large-scale structure in terms of cosmic shear. So if we observe galaxies far away, the same idea, the light from the galaxies will have to go through a lot of stuff to get to us. And the shape of these galaxies could get distorted due to weak lensing. And if you take a catalog of enough of these in the large scale structure, you can again get a handle on what the structure look like and what the neutrino masses ought to be. So down here, just give you an idea of what the current bounds are. So using primary CMB, lensing, and logical structure, the sum of neutrino masses from cosmology now have a very strict upper bound, about 0.16 eV for all 3 generations. And this is an order of magnitude better than what was able to do on Earth in terrestrial experiments like Katrin, which currently puts the bound on just the electron neutrino mass at only 0.8 eV. So it's already like a very big step ahead in terms of what it can say about the neutrino mass bound. And it get even better in the next generation when Euclid, the satellite, which will take a survey of all the galaxies in the logical structure. Once you combine that with CMB, you improve that by almost another order of magnitude, putting the sum of neutrino mass at about less than 0.03 eV. And yeah, at this point, you hopefully that we'll be able to say something about what the sum of neutrino masses could be, because this is below the minimum mass set by the oscillation bands. Okay, so there are a lot to gain, and the experimental front is showing a lot of promise on what it can provide us in terms of data. So then on the theoretical side, we have to follow through with like the correct machineries to analyze this data and try to extract the most out of it. So for us, what we have to understand in terms of logical structure is to find a way to map between what we hope to expect to observe and some fundamental physics parameters. So in this case, the neutrino mass. So for a particular neutrino mass, can we calculate theoretically and predict what kind of structures we should see and what kind of statistical signatures in these structures they ought to be? And to do this, we need to understand the clustering of all matter. So CDMs, baryons, massive neutrinos, plus any other potential matter species or dark matter candidates out there. We have to understand how they all contribute to the formation of the universe. And for this, our focus, we can look at this particular object that's quite popular is the density contrast. So the density contrast for all the matter species is a very useful parameter that just tells us how much stuff there is in this particular location. So at a particular position X, if this is a very large positive number, then it tells you there are a lot more than average amounts of matter in this location. So you have an overdensity, things are clustering here. Whereas if you have a very, very small or very, very large negative number for this parameter, then it means you are extremely under the average in the universe. And that means you have lost a lot of your matter to the surrounding structures and you end up with a void here. And this will evolve in time. And the evolution of this will tell us what is the structure formation doing and how are the matter population evolving. So we need to understand how this evolves to do what we want to do. And in particular, understand how exactly does neutrinos affect the evolution and comes into the picture. Okay, so one thing convenient to do with this is because the density contrast field is, it's got all the information, but it's sometimes a bit hard to kind of quantitatively compare from one cosmology to another. It's a 3-dimensional scalar field. So sometimes extracting a more simplified or a more condensed like summary statistics will make it easier to see what's physically happening. And the power spectrum is a very popular option for this. So it's defined as the 2-point correlation function in your density contrast. So for your matter power spectrum, you look at the density contrast of all matter and you find the calculated 2-point correlation in it. And then you take it into Fourier space and you get this P of K, the power spectrum, in terms of your inverse length scale, the wave number. And you can see a picture here. It nicely summarizes the structure information into this 1D graph. And you can interpret the very small k as the very, very large scales where the big stuff happens. And the very large k is the very small scales. And just to give you a reference, the local group that our galaxy lives in will probably be around k of 1.5. And the Virgo cluster being a lot bigger will be around k of 0.2. And this now, like, you can interpret it as how much structure you would expect on a particular scale. So if we have 2 cosmologies, the blue one and the orange one, and here on k of 0.1, the blue one has a higher power spectrum than the orange one, then you can say that the blue one, you expect to find more structure of this particular size compared to the orange universe. So it's a simple kind of interpretation, and is importantly, very cheap to calculate. So computing this is like relatively straightforward. And okay, a caveat is that there are certain information, like Jia Lu mentioned in the seminar a few weeks ago, that like certain things like non-Gaussianity, where you have to go to high order correlations to find the information, and power spectrum will miss out on those. But in terms of cost benefit analysis, power spectrum is a fantastic starting point, because for how cheap it is to calculate, it includes vast majority of the information. And if a universe is completely Gaussian, it actually contains all of the information. So it's a good place to, as a first thing to check or to look at. Okay, so now that we kind of have an idea what the observables are, so what exactly the neutrinos do? So neutrinos, they affect the structure formation in their kind of unique way, being like a hot dark matter rather than cold dark matter. So they are massive, so they will gravitationally cluster, but also at the same time, they have a large thermal velocity. So there are certain scenarios when they're near smaller potentials that are too weak in terms of gravitational force. They're not obligated to actually cluster or stay with that potential. So here I got my bootleg comic that I stole from Yvonne. So if you have a very small gravitational potential with like small amount of cold dark matter in there, and is not very strong, then a neutrino coming past, we'll look at it, it will probably get deflected a little bit, but the path is not going to be dramatic enough for it to kind of spiral in and actually cluster with this potential. It's just going to go straight past. And also a neutrino, if it happens to be inside this potential, the thermal velocity could be larger than the escape velocity, then yeah, it has no reason to stay here, and it will also stream out of the potential. So these ones you'll find not a lot of neutrinos will stay there, and the clustering is very inefficient on these small scales. Whereas on a larger scale, if you have a lot of cold dark matter that's holding down the fort and generates enough gravitational attraction, then yeah, okay, bad luck, the neutrinos will have to stay there as well. So this produces like an interesting demarcation where you have a particular scale called the free streaming scale, and scales larger than that, neutrinos are clustered just like cold dark matter would. And on scales smaller than that, then neutrinos will become increasingly free and less likely to cluster. And as a result, you get this scale-dependent suppression. So on large scales, you see similar power to CDMs, and on small scales, this becomes less and less power in the neutrino cosmology. And the amount of suppression will depend on neutrino mass. So the heavier the neutrino, the smaller the free streaming scale is going to be. So then smaller free streaming is going to be. So then you'll expect where the suppression, how much suppression happens will differ. So if you go back to this slide where you look at the power spectrum between a cosmology in the blue with massless neutrino and a massive neutrino in the orange, you can see on small scales, you can see a distinct difference between the two, as the massive neutrino cosmology will have less small scale structure due to the free streaming. So sometimes you'll hear this referred to as erasure or the smearing of small scale features. Okay, so that's kind of like qualitatively what should happen. If we want to quantify this, then we need to find a way to actually do some calculations. And this will go to the Vlasov-Poisson system. So we're kind of still doing the same thing. We're trying to understand how the particular matter species is evolving under gravity. But rather than doing it at the level of density contrast, we can take a step back to something more low leveled, which is the phase-space distribution function. It's a distribution function that depends on your phase-space coordinates spatially and in terms of momentum. And you can write down one of these for CDMs, baryons, neutrinos, or them combined. And you can generate you can derive from this like physical quantities like a density contrast, for example. Taking integrals over the momentum will give you the energy density, and then from that you can then construct a density contrast. So we're not doing anything fundamentally different. It's just a slightly lower level object to work with. And now we want to know how this distribution function for, say, the matter species would evolve under gravity. Then that will obey the Vlasov, or also known as the collisionless Boltzmann equation. So here it will tell you how your distribution function will evolve, and gravity enters this term here. And your gravitational potential is sourced by the Poisson equation. So when they couple together, you get your Vlasov-Poisson system. And now this you can then go ahead and solve, and it will tell you exactly how your particle species will be clustering and how the clustering will evolve. But as naive as these equations look, and it's easy to write down, the part where about actually solving it actually becomes a bit of a difficult point. So you can linearize this equation. So here, this coupling will be nonlinear. You see, you have your distribution in here, and you also dependent distribution in this term. So if you linearize the equation, it's relatively straightforward how to do it. But if you go into the very small scales, where nonlinearities and the clustering becomes large, and your density contrast potentially could get to larger than 1, then this set of equations become very difficult to actually try to solve analytically or semi-analytically. And perturbation theory will even break down as your delta is your small quantity in this case. And if delta gets larger than 1, then you can't really rely on perturbative approach either. But now, do we need to go to that small scale though? And the answer is absolutely yes. And to prove why, let's look at an example from the Euclid observables. So Euclid, as I said, was the satellite survey that's going to look at galaxy distributions. And once it takes all the galaxy distributions, we can construct a power spectrum, like a 2-point correlation, but on the angular scale. And I give you these CLs variables here. And these are the source terms in these CLs. And if you look at one of them, it's the line of sight integrals. So like I said, the light from the galaxy will travel along the line of sight to us, the observer here on Earth. And it has to go through all the matter and the clustering in the middle. So this line of sight would tell us that actual trajectory coming to us. And along the trajectory, it has to go through all of these matter density fluctuations described by the transfer function. And okay, the transfer function you can think of as like, it can be related to the power spectrum or the density contrast. So you can think of them the same thing. And this transfer function includes the density fluctuation information depending on scale. And if we look at what Euclid's predicting is forecasting is able to do, it can look at K maximum down to about 6 to 7 inverse megaparsec. And that's extremely small scale compared to what the linear scale is. As you go past K of like 0.1, then you expect the nonlinear effects to actually kick in. And as you go past K of 1, then nonlinearity will be dominant, will be the dominating effect. So in this case, yes, of course, we have to go into the nonlinear calculations. Otherwise, we miss out on a big range of data that will be offered to us by the surveys. And that would be really waste of money and time for on everybody's behalf. So, okay, trying to push to a nonlinear regime have been kind of thought about for a very long time. Perturbation theory can go up to higher orders. So you can add second and third order perturbation theory to solving the Vlasov-Poisson equation. But the reach is still kind of remain well and truly below K of 1. And also even in the quasi nonlinear regimes around K of 0.1, the perturbation theory tend to overestimate the power. And exactly how much you overestimate it by is hard to say until you actually compare it to a simulation. So it's kind of like without doing a proper nonlinear calculation, it's hard to say exactly how well it can do. And then there's also other like Halo model inspired fitting functions like HaloFit and HM code that claims to be able to reach down to K further than 1, K of 2 to 5. But then these require calibration against n-body simulations, which is a nonlinear calculation. So it's kind of like the easiest chicken and egg question you have to answer. Like the n-body simulation being the egg has to come before the chicken of anything else you want to do. So I hope this convinced you that, yes, experimental surveys in the next generation is requiring us to go to the very nonlinear small scales. And computationally, right now, the only method we can rely on is n-body simulations to get a reliable solution in that regime. Okay, so let's have a look at conceptually what an n-body simulation is. So the starting point is exactly the same as the Vlasov-Poisson equation. We're trying to evolve the distribution function under the force of gravity. Like the goal has not changed. The difference is that we're not writing down an equation and trying to solve it. We're kind of taking a more, for lack of a better word, a pictorial approach. So if you take a matter species, be it CDMs or neutrinos or combined together, you imagine a fluid description. So rather than thinking about individual physical particles, you then imagine them to be kind of like a continuous fluid that permeates all of the universe. And local overdensities in the fluid will represent a lot of matter particles clustered in that particular place. And underdensities will represent a void. So once you have this fluid description, The n-body particle then discretizes it back to particles again. So you cut up this fluid into parcels, or represented as point masses in the simulation. But fundamentally, you got to remember is that this forward and backward process, these particles that are discretized now are not the same physical actual dark matter particles or the neutrino particles that you will talk about in like a field theory. These are like a purely like a artificial discretization, and think of them as a particular point mass that samples a phase-space point in the distribution function. So I take one parcel, this parcel represents a particular starting location X and a starting momentum Q. And then I follow the evolution of this one phase-space point, and rather than following the evolution of a physical particle. And if you have enough parcels, enough particles in your simulation, then you sample enough of your phase space volume, then eventually you're going to get a bulk behavior of the species that you're trying to track. So then the simulation takes these phase space sample points, and then they evolve them interacting via gravity in time. And then after some point in time, if you look at the trajectory of these parcels, you can think of them as the same as a phase-space trajectory. So then if the phase-space points started in some configuration, and then after some point in time, they took on a different configuration. And after you take stock of all of them, then you can say something about how the distribution function has evolved after that amount of time. So that is like philosophically what the n-body simulation is doing, is this phase-space sampling and discretization scheme that allow you to describe a fluid without having to sample actual individual physical particles. Okay, the actual tangible ingredients are quite simple. So there are really only three like absolute necessary ingredients in a simulation. So firstly is the simulation volume. So that's where you're going to perform the actual dynamic simulation. And physically, there's really no reason for it to be any particular geometric shape, but a cube is generally taken to be the most convenient. And in terms of cosmological simulations, the size will be around the gigaparsec cubed. Could be smaller, could be bigger, depending on how much you can afford, because the resolution will depend on the volume. The larger the volume is, the more expensive it is for you to get a good resolution. So it depends on like how much you can afford to do. Importantly, it has Pac-Man boundaries, so like a periodic boundary. If you exit one side of the box, you don't get bounced back or anything. You actually re-enter the opposite side. So this avoids weird things from happening. Like if you have a hard boundary or like no boundary, then everything will end up just clumping back into the middle. Okay, now you have the volume and you have to put in the players. The players are your n-body parcels or the particles. And these things in application are just little blips of information in your computer. So your computer needs to know where the particles are, who they are, and what are they doing. So you need to save their three-dimensional position, their velocity, how heavy they are, and who they are. So are you a cold dark matter particle or are you a neutrino particle? Things like that. And you can potentially add more complicated information in there. Like last week when we had the self-interacting dark matter, you probably have to add the cross-section and other information in there too. But with the collisionless cold dark matter simple simulation, these are enough. And finally, you need to have some way of solving the gravitational force between these n-body parcels. Being a small box around a GPC size, you're well and truly sub-horizon. Newtonian gravity is generally good enough. But then if you do want to go into larger and larger simulations where GR effects kick in and you need to include metric perturbations, it's perfectly possible to add it in. So it is something that people have looked into. But if your box is like less than 10 GPC, then like you should be pretty safe to just use Newtonian force. Okay, and now the thing to keep in mind are where the cost is. So these simulations are not cheap. And really it's because of all these things you have to keep track of. So the three main costs is firstly, memory storage for particles. So like I said, these are information that the computer needs to keep track of. So it needs to have them on hand and know what they are and have them ready all the time. So these take up random access memory for the storage. And this will be what, 3, 6, 7, 8 floating point numbers that you have to store. And you have a billion particles, that's like 10 billion numbers that you have to store in your computer. So that you're looking at a ballpark, a billion particles will be about 100, 150 gigabytes of RAM. So that really puts it into like a computation cluster kind of game. You're not going to run this on your laptop. And a billion particles is a rather modest size for a simulation. So in reality, if you look for something that can be used to analyze Euclid data, you'll be looking at trillions of particles. And then also you have processing cycle for calculating these force, gravitational force. The more particles you have, the more force calculation you need to do. And you need to commit more CPUs to actually make this calculation like be done on time. So it's quite common to commit orders of 100 CPUs for a billion particle simulation. Whereas if you go into the big proper simulations like Argon and that runs, looking at 100,000 CPUs is not that strange. And lastly, I think most people kind of forget this, is that the actual time spent on waiting for it to run. So you can set up a very, very detailed simulation and you somehow find the resources for it. But if it takes 100 years to actually compute it, then first of all, you're not going to be alive to see it finish. And second, good luck trying to convince the institution to pay for the power bills. So these things all end up adding up to the viability of a particular simulation or a particular kind of simulation. So just keep these in mind as we go forward. Okay, the most accessible kind of simulation, or relatively speaking, the cheapest one, is what they call cold dark matter only simulations. It's simple because of the coldness of the particles that you're sampling. Being cold, having negligible thermal velocity is fantastic because now your phase space goes down to only 3 dimensions. And having to only sample 3 dimensions is a lot cheaper than sampling 6 dimensions. And your phase space scales only proportionally with the size of the simulation volume. You don't have to worry about what distribution it follows and stuff like that. So in a CDM only simulation, you get a box and you put in the particles that are like almost homogeneously distributed. And you only have to place one particle like on average per spatial location, because as long as you sample this particular X spot with a single particle, you're good. You can just move on to the next location. So this makes it like kind of friendly in a way, like very approachable now that people have been able to scale these up to quite significant sizes and get very good resolution out of these cold dark matter only simulations. This doesn't translate well into neutrinos because, again, of the thermal velocity. So the hot dark matter, the hot nature of neutrinos makes them very problematic. And the 6-dimensional phase space you have to sample sounds like you're going from 3 to 6 is not a lot. But if you just crunch the numbers, you realize that the number of particles required is orders of magnitude more. So again, let's go back in the box where at every single location, you would only need a single cold dark matter particle to sample the spatial phase space. Now for neutrinos, in that one spatial location, you will have to sample the entire 3-dimensional Fermi-Dirac distribution. So conservatively speaking, if you're sampling 6 cardinal directions and 15 momentum bins in each direction, that's 90 particles for each dark matter particle. That's about 90 neutrinos for each dark matter particle, cold dark matter particle you need at every location. And that's a very, very generous estimate. In reality, you'll need like way more orders of magnitude, more n-body particles for neutrinos than to sample cold dark matter. And not just a sampling of the distribution's direction, but also you run into this issue that you actually get process noise from the large thermal velocity of the neutrinos. This one's quite interesting. So let's look a bit more detail on what that means. So neutrinos are like, they can go very fast. So there's a good chance that they can actually cross the entire simulation volumes like side length during a few time steps, especially if you're starting a simulation at very early times. So this neutrino here, of course, cycle tau. So that means that if it's going this way, it will exit this side of the box and then come back in and end up back right where it started in about time tau. And a slightly slower particle will probably take a bit longer, 1.2 tau to kind of cycle around. And a faster particle will take less time, 0.7 tau to cycle around the box. And in absence of gravity, they will just keep doing these cycles back and forth, back and forth. And now, let's look at the spatial correlation. So here, these 3 particles, I placed them in this particular arrangement because I wanted to be that, because this is like what I deem to be the initial physical condition that I have to satisfy. So they have to be this physical correlation with each other. Now, if I go forwards, turn the simulation forward by time step tau, this particle, whose cycle time is tau, it would have went around, came back to exactly where it started, so it didn't move. This one that's slightly slower, so it would have went out that side, came back in, but didn't have enough time to make it back to exactly where it started, so it kind of lagging behind. Where this one that's been faster, it would have started here, went all the way around and overshot its initial position and ended up further ahead of time. So now you see that the spatial correlation is completely different between these two pictures. And all that's happened is that these neutrinos just happen to cycle the box one time. And if we generalize this to a whole box full of neutrinos, whatever initial correlation information you encode in the population, after a few time steps, as they do these kind of volume crossing, they're going to completely destroy any correlation information there are. And you end up with just a box of randomly sampled neutrinos. So they will be Poisson distributed and they will suffer from the Poisson noise. So there are some attempts at reducing the noise in particle neutrino simulations, but it makes it slightly better, but still not enough for it to be a viable option naively, just putting in the entire neutrino population into a box as particles. So the most common way to deal with this is something called a Fourier space neutrinos. So in this case, they kind of avoid the issue altogether and say, you know what, it's too difficult. Let's just not put neutrino particles altogether. And then how do we actually incorporate neutrinos if we don't put them as particles? Well, it turns out you can cheat it a bit and trick the n-body simulation into doing something it's not supposed to. So here we take advantage of the fact that gravitational force is always solved via a potential. So the gravitational potential phi. And this potential is solved from a Poisson equation. And the easiest way to solve Poisson equation numerically is going to Fourier space, because then your Laplacian just turns into a multiplication and you don't have any weird derivatives you have to algorithmically solve. If you have a CDM only simulation, so forget about neutrino particles, they're too hard, too difficult, too expensive. We're just doing CDM particles, you will have this kind of right-hand side contribution to a Poisson potential. And then you inverse transform them back, and then each particle then read off the acceleration from the potential, and they're off and have a good day. But if someone was to come in here and hijack the process during this solution stage in the Fourier space and add in a neutrino contribution to the right-hand side, then when you inverse transform back, the CDM particles will see a different potential. They will see a potential that has neutrino contributions included. So then they will end up moving in a way that they're tricked into moving as if the neutrinos are present, even though we haven't put in any neutrino particles. And the neat part is that the simulation doesn't care where you get this contribution from. Like, you could have rolled a dice and put it in as a random number if you wanted to. It's not going to be correct, but the simulation don't care. So in this case, it allows us to actually derive this neutrino contribution from linear perturbation theory. And that's significantly cheaper than trying to track particles. So instead of having 100 billion neutrino particles to track, we just have to do this integral maybe like 1,000 times for each k value. So this comes from linearizing the Vlasov-Poisson equation for the neutrino distribution. So this gives you significantly cheaper cost for a simulation, and you avoid the whole Poisson noise issue altogether because, well, this is a semi-analytic calculation. There's no problem with neutrino particles at all. So this has kind of been like a go-to method for including massive neutrinos in simulations, where especially if your focus is something like weak lensing, where you care about what the total matter power spectrum, including massive neutrinos, are doing. And in this case, your neutrino calculation doesn't have to be 100% correct. It can be 20% incorrect, but then with the neutrino fraction suppression, F nu suppression, then it will still be 1% accurate in the total matter power spectrum prediction. So this is actually a perfectly viable option. And it's a very rich field in itself, but I'm not going to dwell upon it because in this one, I actually want to talk about particle neutrino simulations. So let's look at why would we want to go further than that if it's perfectly like kind of usable for certain scenarios already. So the reason I want to go further is that there are experiments that want to look at neutrino clustering, nonlinear neutrino clustering in itself, rather than as part of the total matter clustering. So for example, Ptolemy will want to look at how much neutrinos ended up on Earth right here, right now, like in this particular spot. And there are other cosmological probes that will look at the relative motion between the neutrino structures and the cold dark matter structure. And these you will not get from linear response simulations. So you don't have, so neutrinos, they cluster mildly, but then they don't always guarantee to be linear. So the slow momentum bins of the Fermi-Dirac distribution in the neutrino population, they have a potential to actually go very nonlinear if given a chance to, but linear response will miss out on it altogether. And things like Ptolemy are looking for these local overdensities, mostly made up of these slow nonlinear neutrinos. Then you will not get a correct answer using linear response approach. And also linear response assumes that the neutrinos are clustering exactly where the CDNs are. So they're completely in phase with each other. And if they're assumed to be in phase, then you will never get any relative motion. So then you don't get the you won't get the correct answer if you want to use it for probes that look for these kind of relative velocities. So there is a reason to do it. And if we want to do it, can we? Because as I said, we can't afford them. So how can we make the unaffordable affordable? So this is where the approach of like looking for where something needs the resource the most and then exclude the ones that are just there to freeload. And the neutrino population is not so different. There are parts of the neutrino population, the fast end of the Fermi-Dirac, so the high momentum tail. If you think about what they're doing, they are causing all the problems with the Poisson noise with a high velocity. They are creating a large amount of the population that require you to sample, which you can't afford. And they never really cluster nonlinearly because they're so fast, their free streaming scale is huge. So then they contribute almost nothing to what you want to look for. So they cost you a lot and they don't give you back anything. So the most logical thing is to exclude them from the n-body treatment and keep them in the linear response Fourier method and only target the low momentum neutrinos that are actually going to be nonlinear and will not cause you a lot of problems with the high velocity. So then we can achieve high resolution by concentrating the limited computational resources on the subset of the population that really will give us the best benefits of the most kind of return in terms of looking at nonlinearity. So this leads to the idea of a hybrid simulation where we include both the neutrinos as perturbation theory and n-body particles. So this has been attempted several times before by the Danish group and also, okay, this is a bit of international groups, I guess American. So these simulations are pretty nifty. So you start off with purely nonlinear CDM particles, but then purely linear neutrinos. And after the simulation runs for a while, and you realize the slow part of neutrinos are slowed down enough, they're not going to be problematic noise-wise, and they're not going to be producing, and they're going to start producing some nonlinear behavior. And then you pause the simulation, you take out a fraction of the neutrinos that you think will become nonlinear, put them in as n-body particles and keep the rest, the fast ones, as perturbation theory. So then you end up with this kind of hybrid where you're hybriding particle and perturbative neutrinos. So this is like a uber efficient way where you convert where you commit your nonlinear resources to the population that needs it, and only when they need it, and not from the beginning when they're still too fast. And the latest attempt at it in 2018, where they've done it as a 2 Boltzmann hierarchy approach. So they separate the neutrino population into 2 groups. One is a slow group and one's a fast group. And the 2 groups together will make up the entire population. And these 2 groups are each modeled by their own individual Boltzmann equations and Boltzmann hierarchy. And when the time comes, we can then keep the fast group as in their Boltzmann equation and keep them evolving as perturbations, and then convert entirely the slow group into the n-body particles. So the segregation of the Boltzmann hierarchy is because the Danish attempt at it realized that if you were to actually partially cut up a Boltzmann hierarchy and only convert the lower half, you could run into some momentum conservation issues if you're not careful about how you're doing the conversion, and you have to do a lot of reinitialization of your perturbative calculations after the conversion. So this segregation gives you a clean way of saying you guys are going to be particles and you guys stay as perturbations. Now, we come in at this point to ask the question, well, why stop at 2? Since you're segregating the slow part, but the slow part still range quite a large spread of the neutrino momenta. And the optimal conversion timing of them putting them into particles, you would depend on the momentum. So then if you make it as some average, then there'll be some people complaining and some people complaining it's too late, some people complaining it's too early. So if you can actually break it down even finer into n different hierarchies, each one with a narrower range of momentum, then you can actually convert these neutrinos into particles exactly when they need to, and only convert exactly which ones absolutely will be nonlinear. So this relies on this framework we developed, we implemented called multi-fluid neutrinos, and was developed by Dupuy and Bernardo, where the neutrino population is taking the same approach as n different hierarchies and separate them into n different fluids, each one tracked by an individual Boltzmann equation, and they only interact with each other via gravity. So in this kind of partition, you think about each one of them as a semi-Lagrangian independent fluid, independent flow. And it says semi-Lagrangian because spatially they're still kind of everywhere. But in momentum space, each fluid, then rather than being tagged slow and fast, they're now being tagged as a particular momentum value sampled from the Fermi-Dirac distribution. So you think about it as taking the Fermi-Dirac distribution, breaking it down into momentum bins, and then each fluid gets a particular bin label to say you're the slowest one, you're the second slowest one, you're the faster one, et cetera, et cetera. And so each one represents a particular part of the Fermi-Dirac. And then each individual flow is then modeled by their own Boltzmann hierarchy with n mu number of Legendre multipoles. And it looks fairly similar to what you expect from a standard your continuity and Euler equation, with some slight quirks, in particular to the multi-fluid scheme. And in particular here, you see the Lagrangian velocity that is related to this Lagrangian momentum of breaking up the Fermi-Dirac. And the index, as you can see, the alpha index is the fluid flow, so which flow is it? And L is the which multiple we're looking at. And the multiples, of course, coupled to each other. But you see, the fluids are all coupled only to themselves. So each individual independent flow are only intercommunicating with each other via the gravitational potential. That gives it an advantage that if we delete one of them and turn them into particles, it doesn't disrupt any other fluids equations of motion besides their contribution to the potential, which it doesn't care how you contribute, as long as you contribute somehow. So yeah, as an example here, we show you, like, we picked a model, which is the Planck 2018's base cosmology, with a fairly heavy set of neutrinos, about half an eV sum of masses. And here we broke down the neutrino population into 20 fluid flows. And here at Z of 0, you see the dimensionless power spectrum. And the very fast flows on the red end, they're very fast, so you don't expect them to cluster a lot. They have very small power and they remain well and truly linear. The slower fluids that are see a lot more growth as they are slower, so they're more prone to gravitational clustering. And you see some of them, these dashed lines, the dashed line at 0.1 indicate that where nonlinearity might become important. So as the fluids approach 0.1, these fluids will have nonlinear contributions in their clustering behavior. And once you cross 0.1, you expect the nonlinear effects to become more and more dominant. And so we want to investigate between like this top half of the population, where the slower half, where these fluids have the most, show the most potential that they could potentially show nonlinear clustering. Okay, so just to say a bit about how we do the conversion. So the conversion can happen at any time you want. So you pick a particular intermediate redshift that's between the start of the whole simulation and the end of the simulation. You pick a redshift and want to essentially pause the simulation and put the particles in. You delete the fluid flow from the multi-fluid perturbation system. So then you make sure you don't double count them. And the deleted fluid flow will then be replaced by n-body particles. So a collection of neutrino particles put into the simulation. And now these particles need instructions on what they're doing because the multi-fluid has been tracking their behavior up to this point. So you use the multi-fluid information up to that point as the initial instructions on what the particles should be doing in the first time step. So the density information tells you how they should be correlated density-wise. And the theta, the velocity divergence, tells you how the initial velocities should be. And we assume that the initial phase follows exactly the CDM particles because, well, the perturbation theory assumed they're completely in phase. So it seems like a very good place to start. Then the two questions to ask here now is, when do we perform this conversion? So this choice seems free, but like I said, there are a lot of considerations. You can't convert them too late, or you miss out on nonlinearity. And if you convert them too early, they're still too fast. They become too expensive for you. So when to convert, and also question who to convert. Out of the 20 streams, we say these show potential to cluster nonlinearly, but who actually contributes enough to warrant the treatment, because this is expensive. We don't want to convert them unless we absolutely have to. So these two criteria we have to establish and answer. Okay, so conversion timing, like I said, ideally you want to convert them as late as possible. So you wait for them to become slow enough that they're not problematic in terms of the numerical noise, and they about to exhibit nonlinearities, so you don't miss out on anything, but then also you don't convert too early. But with n-body simulations, always is concerned that if you convert too late, that the particles will end up having some numerical artifacts encoded in them, that it will take time for the simulation to smooth it out. So you can't actually delay this exactly as late as you would ideally like to. So we can see here, if we convert the stream at redshift of 19 down to 9, down to 5, compared to the very high redshift conversion, converting a redshift of 5 at very late, you end up with these unnatural physical transients, these peaks that don't correspond to anything. So these are non-physical artifacts. And as you go earlier and earlier, these artifacts die down because the artifacts are given time in the simulation to resolve themselves. So it turns out that these artifacts come from the choice that we made to only use the monopole information to initialize the neutrinos. So the neutrinos, each fluid flow is tracked by a large number of multipoles, and the higher ones will include the anisotropic stress information. But we're only using the monopole to initialize them. So then the neutrino population, the n-body population, must regenerate its own anisotropic stress during the runtime. So this takes simulation runtime. So you need to convert them early enough so then they can regenerate their own higher order moments. The way to solve this is to add in these high order informations, but at present time, it's not obvious how you would do that without breaking the bank. So a rough estimate here is that you have to start about Z of 20 for the slower flows that are very nonlinear. And the quasi-nonlinear ones can be started slightly later at redshift about 10. But later than that, you'll start running into these issues. So the second one to ask is which one actually deserves to be converted. So you can only qualify if you show you can produce enough nonlinear enhancements. So can we find out something about which one will be nonlinear without having to try and error this every single time? And for the Neo5 model, again, we converted the first 14 out of the 20 fluids, and we plotted their nonlinear versus the linear results. So dashed line is the linear response result, and the solid line is the nonlinear n-body result. And you can see the slowest flow, the first two flow, the slowest two, exhibit significant nonlinearity, about a factor of 10 enhancement at about K of 1. And the faster ones, flow 11 to 14, these are like at the tail end of the Fermi-Dirac. They do absolutely nothing. They just track exactly what the linear response is doing. In fact, the only thing that's different about them is that the Poisson noise floor kicks in a lot earlier. So they suffer from Poisson noise and they don't offer anything. So you would not be converting these ones. But the first 6 streams, you can see there are clear nonlinearity enhancements that you would be missing out on if you were to keep them as linear response neutrinos. So taking the amount of enhancement that we expect, that we see in this trial run, we were able to find a linear mapping that's quite interesting. So if you look at the linear response power spectrum at Z of 0, and you find where do they peak. So this one, for example, peaks around 0.1, and the 3 to 4 fluid flow peaks slightly lower at 0.05. And the really fast ones peak lower at 0.01. And then you look at how much nonlinearity over the linear response counterpart you expect at K of 0.5. You can actually map them by this linear relationship very well. So, okay, I don't have to plot for it, but if you plot the points, this level, this delta square max can map to the amount of nonlinear enhancement you expect in a perfect straight line. So that's good, because if this thing holds, then I don't even need to run the simulations first. I can look at the linear response results and already be able to predict, okay, this one's worth it, this one's worth it. these two are not, so I'm not going to touch them. So that gives me like a way to make these decisions without wasting any resources. And so we tested on a different neutrino mass and say, okay, this might work for half an EV summer neutrino mass. Does it actually work for other neutrino masses? So we reduced the neutrino mass down to 0.3 EV, and we look at the linear response results. And here for the first 3 flows out of 20, they peak at 0.09, 0.04, 0.025. And then we run the n-body simulation and look at how much nonlinear enhancement they see at 0.5. The color lines are the nonlinear n-body results, and the dashed line is the prediction made by this fitting function. And you can see they match actually perfectly. So this function is mass independent of neutrino mass, able to tell you how much nonlinear enhancement to expect given the linear response behavior of the particular neutrino flow. Okay, so in summary then, so we're now using multi-fluid as a foundational platform of segregating the neutrino fluid into these independent flows. This facilitated a method of being able to fine-tune exactly which neutrino hybrid to convert to n-body representation. And we can control it to exactly when to convert them and which one to convert, completely free up to the user's choice. And the nonlinear enhancement can be now predicted from just the linear response results. That means that we can establish the eligibility of a particular flow for conversion without having to try and error every single time. So that can be very useful later to give a particular neutrino mass. You can look at the multi-fluid decomposition and ask if a particular flow will be worth the effort to go further into the hybrid scheme. To going forward though, as we said, the redshift conversion eligibility is slightly kind of disappointing in a sense, the fact that because of this high order moment information is missing, then it forces us to convert a lot earlier than we ideally would like to. So in the future, if some way has to be kind of investigated to how to actually include these anisotropic stress and high order information into the initialization procedure. And also the initial neutrino phase, we assume that to track exactly the CDM or the total matter phase. That's not the worst starting point, but then a priori, without any proof, there's no reason for us to believe that is exactly how it should work. So in the future, we need to work out exactly how to track the phase to know if the phase is actually going to be different or if it being the same is actually a good assumption. And if not, and if we need to implement a different kind of phase, how do we actually physically do it? So yeah, thank you for your attention, and I'll leave this here.
Yeah, thanks a lot, Joe, for a very interesting talk. Now we have time for questions. Who would like to go first? Maybe while everyone is still thinking about questions. So what is the optimal number of different neutrino fluids? So you basically showed something with 20. Is there some optimal number? Is it basically more cost expensive to have more fluids, or?
Yeah, that's a good question. So the multi-fluid decomposition have where is it? So it has n tau number of fluids, and each fluid will have n mu number of multiples. So if you increase the number of fluids, it does put more computational costs because you have to track more equations. We did do a study in the multi-fluid paper and found that if you compare a single Boltzmann hierarchy, like a class calculation for neutrinos versus the multi-fluid, higher than 10 fluids is enough to get you percent level accuracy. 20 fluids is perfectly sub-percent level accurate. If you add more, it will be purely for the reason of gaining finer control over the conversions. But in terms of the linear response, the linear perturbation theory accuracy, 20 is like a sweet spot for us.
Okay, thanks. Yeah, there's a question by Chris.
On that one slide that you had where you had those 2 dashed lines, back a little.
Oh, this one?
Yes, that one.
Yeah.
So I wasn't quite sure what's the difference between those 2 dashed lines.
Oh, it's just it's a kind of, I couldn't figure out how to use shaded in GNU plot, but it's meant to be like this shaded region where like above this, as you're approaching 0.1, then you're starting to be suspicious that you might be nonlinear. So we're saying fluids that go above this are worth investigating to see whether they will exhibit nonlinear clustering.
I see. And then above 0.1, it's clear that they're definitely nonlinear. Is
Yeah,
that,
yeah, that's right. Yeah, so it's technically like a cutoff line, not a actual physical line.
Thanks.
No worries.
Maybe I can ask.
Yes.
How much of your code is specific to neutrinos? Could you do it for other forms of hot dark matter?
Actually, yeah, that's you don't have. There's nothing neutrino about this. The Fermi-Dirac distribution is the only thing that's specific to neutrinos.
Yeah.
So we have actually done a version of the multifluid code where the sample is done from a Bose-Einstein distribution, so you can do it for axions.
Yeah.
And the rest of the workflow, yeah, it's nothing particularly neutrino-y about it.
Oh, cool. Okay. Yeah, that might be quite interesting for like a like hot thermal axions produced in the like EV scale axions or something. I don't know. Yeah, that'd be cool.
Yeah. This could be translated to non-neutrino applications quite easily.
How far away are you from comparing it with like observations? Is it the kind of thing you're waiting for like Euclid and stuff, or?
Oh, yeah. So somebody has to, like a actual supercomputer center has to pick up this idea to run a big one because.
Oh, yeah. Okay.
Yeah.
Oh, and could you comment a bit more about the Ptolemy and the clustering? Because I guess do you expect there to be like significant enhancement in the like relic neutrino density based on what I know people usually consider or something, or is it more that's the direction this is sort of would eventually head in? Yeah,
so with Ptolemy, it comes with the additional complications that you have to do like what they call a constraint simulation, because you need to actually get your background, CDM background, to look exactly like the local group. And so ideally what you do is that you run a simulation where the CDMs are set up so that it is exactly what like the Virgo cluster and the local group look like. And then you run this hybrid neutrino on top of that simulation to see how many end up on Earth. If the slow neutrinos like show factor of 10 enhancement like this, then yeah, I don't know exactly how much difference, but hopefully it will be something that it should be something that you can like see a discernible difference at least. So it depends a lot on the phase of the neutrinos again. So yeah, I don't know until I run it.
So in the beginning, you mentioned you can probe the mass hierarchy, so the mass ordering for neutrinos. So what's the time scale when cosmology can say something about it? I'm just interested in how it does it compare to oscillation experiments.
I think for cosmology, right now, the most straightforward way is just to hope for that the mass bound, the upper bound, go below the inverted hierarchy. But there have been. Okay, I'll be honest, I didn't quite understand that paper, but there was this paper that was talking about neutrino wakes. So if the neutrino kind of crosses with a cold dark matter structure, like the way that the wakes form in those neutrino fluids will be different depending on if it's a that's different. That's something else. No, I guess then the other thing is No, I'm thinking of something else completely. Sorry, ignore me. No. Yeah, as far as I know, you have to wait till the upper bound goes down.
Yeah, you have to wait until the upper bound goes on. So you have to wait till Euclid, or is there is there any other data coming which can?
I think Lyman alpha has been promising some tighter bounds than CMB if you combine with LSS. So marginally tighter, but yeah, I think Lyman alpha probably be able to. Given that Euclid is kind of what's it called? Not sure when it's going to actually start. So if I had to bet, maybe I'll say Lyman alpha will be able to get it slightly sooner.
Yeah, thanks. Any other questions? Maybe let me ask you one more about the binnings. So you said basically, okay, you bin it in those 20 bins or so, or however. many. So what would happen if you basically shift the boundary of the bins? Does that affect it, or so basically if you if it's slightly offset, also if you change the binning, are there any effects you see in the simulation when you change that?
I don't know actually, because the binning scheme we take here is just that each stream will have the same number density as each other. So some bins are wider than others in terms of the momentum range.
Okay. You don't keep the momentum range fixed, or so it's really just the number density of neutrinos.
Yeah, but like fundamentally, there's nothing like forcing you to do it that way. Like you can bin these any way you want. So you can even do like a log binning if you want high resolution in the lower end. I don't think we did any tests on that, so we don't know how it would, like the convergence probably needs to be tuned up to a certain number of bins before it doesn't do anything weird.
I think the short answer is yes, right?
Yes, it would change.
Yeah, it would just depend on whatever is your representative momentum or average momentum in that bin, right? Then and if it's lower or higher, that will shift the line up or down because high momentum, less clustering, so the line goes down.
Okay, yeah. The line.
That's what I would generally expect if I'm looking at the lowest bin.
Yeah. So I'm just wondering then how the final result depends on that, or whether you can basically put an upper bound on that those effects due to binning or due to those whether they are smaller than whatever sub% level or whatever you want to achieve.
Well, ideally, what you want to do is to determine a set of criteria of what you want to convert and what you don't want to convert. And those ones that you do want to convert, you throw all your particles at them and bin them as finely as possible, and then do convergence tests until you hit the sweet spot of your computer can handle it. You get an answer that's within whatever tolerance you specify. Yeah. But beyond that, I don't know. I don't think that's like a fixed rule of how to do it, how to bin.
Yeah, I guess it depends what you want to achieve in the end.
Yeah.
I guess the hardest part about these things is like there's nothing for you to compare your answer to know if you're on the right track or not. Like, because everything's kind of unexplored territory. So yeah, different binning. Like, there's nothing else to use as a benchmark to tell you if your scheme is on the is correct or not. So you can only achieve internal convergence. That's the most you can say.
So you compare different simulations which you have to each other and see whether it's consistent and so on.
Yeah, even that's hard because the numerical difference between codes are generally on the level like 5 to 10% without control. So like, yeah, it's very difficult to even do that.
Okay, no, that's interesting. Thanks. Any last question? If not, then let's thank Joe again for a very interesting talk.